Howdy.
Howdy.
Welcome to this special seminar in the occasion of the grade 3 Carroll Young Investigator Award. We're delighted to have that award recipient, Rina Barber, amongst us. She's a professor in the Department of Statistics at the University of Chicago. Before starting at the University of Chicago, she was an NSF postdoctoral fellow during 2013 at Stanford, supervised by Manuel Candice. She received her PhD in statistics at Chicago in 2012, and then MS in mathematics at the University of Chicago in 2009. Prior to graduate school, she was mathematics teacher at Park School of Baltimore from 2005 to 2007. Her research spans many areas of modern high-dimensional statistics and machine learning, including regularization, false discovery rates, predictions, graphical models, and many others. She has received many awards, including the 2016 Sloan Research Fellowship, the 2017 Tweedy Award from IMS, 2020 Cox President's Award, and the 2023 Carroll Young Investigator Award. So today she is going to talk about stability of black box algorithms. Yes, welcome.
Thank you so much. Thanks for the introduction and thank you for the invitation. It's such a pleasure to get to be back at this great department. I was here for a workshop many years ago, i.e. before lockdown, and it's just really fun to be back. And I'm also so honored to get this award. I'm a huge admirer of Dr. Carroll's work on high dimensional statistics and measurement error and semi-parametrics and so many more areas, and just thrilled to be here. So thank you so much. So this work is actually two projects stuck together into one talk since they're on related problem on stability. So I'll define what that means in a minute. I just want to say that a lot of this work is very new. The second project is just a few months old. I would absolutely love your feedback, so please feel free to jump in anytime with questions. Looking forward to hearing your feedback on this work. So today I'm going to be talking about two problems that are both in algorithmic stability, which I'll define in a second. The first problem is a negative result. We tried to create a test that would determine whether an algorithm was stable, and it turned out that actually we found that it's not possible. So the first project is about a hardness result, understanding why it is that measuring algorithmic stability is challenging. The second project is going to be a positive result about stability in the setting where we use bagging. So methods like bootstrapping or other ensembling methods, they actually turn out to have really nice properties in terms of stability. So I've been super lucky to get to work with some wonderful collaborators on these projects. The first project, the hardness result, is joint with my former PhD advisee, Byul Kim. She's now at University of Washington. The second project has been driven by a postdoc, Jake Soloff at UChicago, who works jointly with Rebecca Willett, my colleague, and with myself. Okay, so let's get started. So I'm going to start by just introducing and motivating algorithmic stability. So sort of why do we care? Like, why are we trying to test this? Why are we trying to establish this? And I'm going to talk a little bit about how algorithmic stability implies other things that we're maybe more familiar with and more motivated by, like generalization and statistical learning theory, predictive validity if we're trying to do inference, and things like that. Then I'll move on to the two projects. Okay, so what are we talking about when we talk about algorithmic stability? So generically, I'm thinking of an algorithm A as any procedure that inputs training data and outputs some kind of fitted model. And that fitted model is just whatever regression function you have. So it could lie in a specific class. So it's like some linear function of X to predict the value of Y, or it could be much more non-parametric or over-parameterized. So we are going to think of A as some black box procedure where I feed it data and out comes some fitted model. And I don't necessarily know exactly what's going on under the hood. Now, why do I not know? Maybe because it's something super complicated. So it's some kind of deep neural net whose architecture I'm not even 100% familiar with, or it could be that I think it's quite simple. Maybe it's just a lasso, but inside of it, it has some default settings where it like standardizes the variables, and I don't exactly know what it's doing. So there's lots of settings where we may not necessarily want to commit ourselves to knowing exactly what the algorithm does, but we know it works well. It's sort of, something we've used in this application before, and we'd like to understand its properties. Now, if we're willing to make more assumptions, and this is both on the data and on the algorithm, maybe we can try to answer questions like, does the output, the fitted model, actually correctly estimate the true distribution of Y given X? So maybe this would be a setting like, I assume that y given x follows a Gaussian linear model, and I am using least squares, or I am using ridge. So I'm being very specific about the distribution and also about what algorithm I'm using. But as I get more flexible, maybe I don't want to assume that my distribution is Gaussian linear, because when does data ever exactly satisfy that? Or maybe I want to use some complex package that someone else implemented and I don't exactly know what the algorithm does. I want to give myself more flexibility, both in terms of what algorithms I can use and what data I can handle. So then we start sort of moving down this hierarchy of like what types of things we might expect to be able to say. So first of all, maybe there isn't even a true model of y given x that I'm willing to assume, but it's still the case in many settings that I could give guarantees that my fitted model could predict y with low test error. So maybe here I might relax from saying the true model is Gaussian linear to just saying something like the true model is close in some sense to the space of linear models. But if I remove more assumptions, then maybe all I'm able to hope for is something like generalization. Is my model, when I look at how well it does on the training data, going to perform similarly well on test data? Or am I overconfident due to issues like overfitting and things like that? So can I have generalization? And maybe even weaker, maybe my model overfits on the training data. Maybe it's something overparameterized enough so that it actually interpolates and trains down to 0 error on the training data. So can I still, however, find some way, maybe cross-validation, to tell you how well will the fitted model predict y from x on future data? So can I at least give you an estimate of the quality of my model, but I don't necessarily need to assume generalization or some kind of specific parametric model or anything like that. So as we move down this list, this is sort of a general overview of like what people might ask in the literature with more assumptions versus less assumptions. As we move down this list, often if you look at papers that sort of head towards the bottom of this hierarchy, the least assumptions, sometimes the last assumption remaining is an assumption of algorithmic stability. And that's why we're so interested in it, because it's often treated as something that is a much weaker, sort of friendlier and safer assumption in place of assuming things that maybe we never know if they're true, like parametric models for our data. Okay, so what are we talking about when we talk about stability? First, let me just explain it informally. In a high assumption setting, we might have something like concentration or consistency, where we assume enough conditions so that when I run my algorithm, f hat concentrates around some true f. So like I believe the linear model and my beta hat is very close to the true beta or something like that. But in a more weak assumption setting, we might instead have something that's a weaker statement, the second statement here, that if I were to resample just a small fraction of my data, the estimate that comes out, the fitted model that comes out, stays roughly the same. It doesn't massively change just because I change, 3 images in my training set or something like that. So we can see that if we have something like consistency, that would imply stability, but consistency is much stronger. It says that even if you resample the entire data set, you're going to basically get the same answer. Whereas stability says, well, that might not be realistic, but if I just resample a small fraction of the data set, will I still get a similar answer? All right, so now let's formalize this. There are a ton of different definitions of stability in the literature, depending on sort of what downstream application we'd like to use it for. So in this talk, I'm going to be focusing on one particular style of definition. And this definition says that if you have data from an unknown distribution, sorry, where's my pointer? There we go. If you have data from an unknown distribution, let's say that I train f hat on the entire data set, so n training points, versus I train f hat remove I, so f hat minus I, on the same exact training data set, but with one data point removed. So I pulled out one image from my training set. Is it the case that the prediction I make on a new test point, xn plus 1, is going to jump by more than epsilon? And stability requires that the chance of that happening is at most delta when your data is IID from a distribution. So I want to point out that this assumption of stability is actually a statistical flavor of assumption. It's not just an assumption about an algorithm. It's assumption that this algorithm paired with this particular distribution that your data is coming from leads to this property. So this is an assumption that's actually on the pair A and P together. And one thing to notice here is that the data is assumed to be IID, which means that when I remove the ith training point, I'm removing a training point at random. So this is not assuming too much. It's not assuming that you can search in your entire space of like 10 million images and find some really influential one and remove it and still require stability. That would actually ask a lot. This is saying that when you remove one at random, you are requiring stability. So it's a weaker condition. Okay, so throughout this talk, I'm going to assume that the algorithm treats training data symmetrically, meaning that if I feed it these 10,000 training points in a different order, I'm going to get the same fitted model coming out. And also here, oh yes, go ahead.
So the probability with respect to the measure,
Mm-hmm.
is it not also with respect to that randomization of choosing that part?
That's a great question. So those are actually equivalent, whether you write it that way or not, like whether you write it over a random I or a fixed I. And the reason is that because the data is IID, taking out the first one is equivalent to randomly drawing an index I and taking out the ith one. So specifically because the data is IID, it doesn't matter. If the data set was deterministic, which is actually the format of this assumption I'll be working with in the second half of the talk, if that were the case, then you would have to say that I'm going to average over all of the possible I's and sort of treat the I as random. So you can equally think of it that way. Thanks. Other questions? Oh, okay, so let me just point out that here, just to keep the notation as light as possible in the talk, I'm going to be writing the functions as though they're a deterministic procedure applied to the training data, so like least squares. But the framework and results can pretty easily be adapted to allow for a randomized algorithm. So like something you trained using stochastic gradient descent, for example, or something where you use bootstrap, so you have like random subsamples in your data. So randomization is totally fine. The notation is not going to reflect that just so that it can like fit inside the slide. Okay, so I talked about sort of what stability is for, but let me formalize this a little bit. And this is a huge literature. So this is really just a couple of applications and a couple of references. So stability has implications for generalization. I'll go into more details in a moment. So basically, can I tell you based on the training set how well it will do on the test set? It has implications for learnability. So whether it's possible to use the data to learn a rule that will drive the risk down. It has implications for predictive inference. So can I build predictive intervals around my prediction that are guaranteed to actually cover the noisy Y that you're about to observe some desired fraction of the time? So let's go into some of these in a little bit more detail. Okay, so generalization first. So if I have a trained model F hat, so again, this is trained on my sample of size N, what I'd like to do is tell you how well will it perform in future. So here the loss L of F, or the risk, is the expected loss when in future I draw an XY pair, I use F of X or F hat of X to predict Y, and I have some kind of loss. So this could be like squared error, 0, 1 loss, something like that. And I can also try to estimate this based on my training set using either the training loss, but oftentimes that's a huge underestimate due to the problem of overfitting, especially if you have an over-parameterized model. I could also use this leave one out loss, which is a cross-validation style approach, which says for each training point, let me retrain my model without the ith training point included in the training process, and then let me ask how well did it do for prediction on the ith point. So this just averages over all I. And so here's our leave one out estimate of loss. So it's much more realistic to hope that this estimate would do a good job of telling you how well the function will do in future than the training error, because the training error could just be 0, but that's not realistic for how we'll do in future. And what we know from the work of Bousquet and Alassif is that under certain conditions, if you have a version of stability, so this version of stability is really similar to what I had on the last slide. Basically, the leave one out model has a similar loss on a typical test point as the fully trained model. If that's the case, then the generalization statement holds when I'm trying to figure out how large is my future error, and I'm estimating that based on my leave one out error. So this shows us how stability leads to an ability to say how well will I do in future. Now, this is very closely tied to predictive inference. So predictive inference says, don't just tell me what risk I'll have in future, actually give me a predictive interval that should contain the Y value, so that I can say sort of like, this patient's symptom level will be between like this value and this value, and I should cover the true Y some fraction of the time, so 1 minus alpha of the time. So distribution-free prediction is the problem of constructing a prediction band based on training data so that regardless of the training, regardless of the data distribution, you will have this coverage guarantee. So we might be familiar with holdout methods or conformal prediction style methods that are distribution-free methods to try to achieve this goal. And one other option is to use jackknife or cross-validation style methods, which are basically like a data-efficient way to avoid having a holdout set. If your sample size n is pretty small, I'd like to not split it in half to have a holdout set to tell me how wide I need to make my prediction interval. Instead, let me use something like cross-validation or jackknife, leave one out cross-validation. So this is what jackknife looks like. As before, I'm going to train a model on the entire training data, and I'm also going to train all my leave one out models. And then for my prediction interval, one way to construct it is to say that I'm going to center it at my prediction at of x, and then plus or minus what margin of error. So let's say I want 90% coverage. What I can do is I can take the 90th percentile of my leave one out residuals and say that that's a pretty good proxy of the 90th percentile of my future test errors. So let me use that as my margin of error. And there's work in the literature by Steinberger and Leib that tells us that if the algorithm satisfies stability, then you don't need any further assumptions for this to be a distribution-free valid interval. So effectively, you have no assumptions on the distribution P directly, but you do need to assume algorithmic stability. If you don't assume stability, you can actually construct degenerate scenarios where the trained model versus the leave one out trained models behave completely differently. And you would get even like 0% coverage for this predictive interval because of that degenerate behavior. So this is an example where stability is like the last condition standing. We sort of remove all distributional assumptions, but we still need to assume stability for this very practical and intuitive method to have a theoretical guarantee. Okay, so what are we seeing at a high level? What we're seeing is that basically, like in statistics, we want methods that are valid with the minimal possible assumptions for us to feel reassured that things are going to work in practice. And distributional assumptions make sense for some settings. There are some settings where we know the data behaves nicely. But in settings where data is complex or super high dimensional or maybe just really scarce, so it's hard to test distributional assumptions, we don't want to necessarily trust that that parametric model is true. And oftentimes distributional assumptions cannot be tested. So basically, like we have a goodness of fit test, say, but it only detects certain types of deviations from the model. So maybe we don't want to rely on distributional assumptions. And so there are methods that are more robust, something like using jackknife for predictive inference rather than using like a formula for a parametric prediction interval. But they instead assume that the algorithm A is stable instead of placing assumptions on the distribution of the data. And the fundamental question that we reached here is, can I verify that A is stable? Because like I cannot verify that P is smooth. That's something that's untestable. Can I verify that A is stable so that I feel comfortable with this weaker, more robust option? Or is asking the question, is my algorithm stable, another untestable assumption? And if that's the case, should we be worried? Because effectively, like, have we just replaced one untestable assumption with another untestable assumption? And maybe we aren't that much better off than we were before. So it really depends on what setting we're in and what algorithm we're using, because we'll see in a second that some algorithms are stable by construction, but other algorithms are too complex. And that's where the question of like, can I test whether it's behaving in a stable way? That's where that question becomes really relevant. Okay, so what's stable and what's not stable? So maybe we're okay because actually there's a number of algorithms that are stable already, like stability is built in. I don't have to test it, I just know it theoretically. One example is nearest neighbors. If the number of neighbors, k, is much smaller than the sample size n, the reason this is stable is simple. The question is, how much does my prediction change when I remove one training point? And remember, it's one training point removed at random, not adversarially. So if I remove one training point with overwhelming probability, it's not one of the nearest neighbors of the test point, and so my prediction doesn't change at all. So this is actually extremely stable. Another example is ridge regression, or more broadly, anything that's regularized with a strongly convex regularizer. The reason is that if you throw some Lipschitz assumptions on the other pieces of the problem, the strong convexity in the regularizer means that when you remove one term from the empirical risk that you're minimizing, that can only perturb the problem by so much, and the solution can only move by a bounded amount. So as a result, your prediction when you plug in the solution beta hat also only moves by a bounded amount. So this is another example where stability is baked in. It's already guaranteed just from the theoretical properties of the method. But those are really simple examples. And so we might ask first, like, are there simple algorithms that are already unstable? And second, what about complex things that people are actually using now, like state-of-the-art algorithms for different applications? So first, this is the plot that really convinced me we need to study stability. This is literally just linear regression for data that's generated like IID Gaussian. So this is just about as clean of a simulation setting as you can get. So in each of these plots, on the x-axis is my prediction, and on the y-axis is my prediction for the same test point when I remove one training point at random. So in the setting where d is 100 and n is 500, you can see they cling really closely to the diagonal line, meaning that the perturbation is tiny, and at least empirically, it looks like stability holds. They're like no more than epsilon away from the diagonal line most of the time for some very small epsilon. However, when d is 100 and n is 105, so we're really, really close to the d equals n regime, you can see that now the spread around the diagonal is enormous. So we actually have massive instability. And again, this is just for least squares. So here we should be worried because basically the sort of simplest algorithm that's the theoretically most easy thing to analyze that we know is already exhibiting instability. Now for least squares, there are beautiful characterizations of exactly why this happens. And effectively, it's because here the design matrix is nearly square. And for a square matrix with IID entries, its condition number is really poor because the lowest eigenvalue goes down to 0. So we know why this happens. But in a more complex algorithm, we might not know why this happens and if this happens. And so that's where the question really kicks in. All right, exhibit B. So what about modern machine learning algorithms that have many layers and complicated strategies to make things work better? Do we know whether it's stable or not? And so for something like this example in that field, I would argue that probably it's going to be extremely hard to have any kind of theoretical guarantee of stability, basically because a lot of the theory for the methods is developed much slower than the methods themselves are being developed. It's hard to keep up. And so theoretical guarantees that we have for neural networks and deep learning often study cases that are like much simpler than what's actually being used. So like, let's study something with 1 layer or 2 layer or something like that versus what's actually being used. It's going to be very hard to prove stability for whatever is actually the sort of state-of-the-art cutting-edge algorithm used in machine learning. Finally, going back to things that are more classical, I noticed an interesting phenomenon when I sort of went digging in the code of some R packages. So we might ask ourselves, like, why would something like Jackknife not work? Why would stability fail? Because would it really ever be the case that training on 100 things is completely different than training on 99 things? And the counterexamples for all of those questions is like, well, what if I do this? If your training size is even, run least squares, and if your training size is odd, run a neural net. Then of course, like the prediction you get at sample size n versus n-1 are totally different. And the very natural question is like, yeah, but when would that actually happen? But when I actually looked into the code of some R packages, there's actually quite a few examples where the like default parameter settings change when the sample size jumps above or below a threshold. So here's just a few examples for lasso, a variant of lasso for imputing missing data, which is basically just saying that like if your n, if it jumps above or below a threshold, change some default setting. I don't actually know whether this would empirically create instability, but it's at least the case that sometimes you really are running a different algorithm at sample size n versus at n-1, but we think we're running the same algorithm because we're calling the same function. So all of these things motivate why we need to understand, can we test stability, or is it just an assumption that we sort of hope is true? Okay, so let me pause for questions and then I'll move on to our first project. Yes.
It might be some kind of philosophical question.
Go ahead.
Okay, yeah, so like personally what I feel is like, for example, if you have an algorithm that like we want to see whether it's kind of stable or not, and it depends on kind of what losses and those kind of things we have. Like personally, it feels like it's kind of cyclic, because what it means by cyclic is that like if like we kind of construct the robust laws to make a stability or like vice versa, I guess. So I think it's kind of more depends on like what our law suggesting. So like without any information of laws, I'm kind of doubt why you can kind of show some kind of stability.
Yeah, I understand what you're saying. So actually what we're working with in our work is stability on the prediction itself rather than stability after you've applied a loss. So we're looking at, sorry, backing up frantically here. We're looking at this definition where you're actually looking at the raw prediction. And so there, like, there's no opportunity to use a loss to sort of like reduce that in some way. But you're right that in a lot of the literature, you end up with you end up only needing conditions like this, that maybe the prediction moved, but the loss didn't move very much. However, I would argue that even though clearly like the first version implies the second version and not the other way, I would argue that in any practical setting, it kind of goes both ways. Because if your loss is hugely insensitive to the first argument, then the loss is not actually meaningful, right? Like if the loss is kind of roughly constant when the prediction changes, what am I really measuring? So if instead the loss is like, let's say locally linear or something like that in the first argument, or in any case does depend on the first argument in a meaningful way, then if the first argument changes by a lot, the loss will also change by a lot. So because this is not, because the absolute value is inside the expectation, you need the loss to stay the same for like individual data points rather than like allowing yourself to average and then take the difference. So I think to some extent, it would probably be challenging to find a setting where like you could choose a loss that makes things that were highly unstable suddenly stable. It could certainly change by a bit, but I think fundamentally, if it's hugely unstable before you pass it through a loss, it will still be quite unstable after, if the loss is actually reflecting the quality of the prediction, I think. Thanks for the great question. Yes.
Question about your observation regarding the passport, that example you were talking about. So I can clearly see, of course, if you're changing the definition of the algorithm itself in terms of the sample size, probably could cause instability. But let's say I use exactly the same, I don't know, parameterization for every sample size. Is it still going to cause instability because of the shrinkage effect of the L1 penalty in some sense?
That's a great question, and I don't know the answer. So for least squares, which at least is like a subset of lasso, if you set lambda to 0, like we can see here that instability does happen. Whether you could guarantee for lasso with like a positive lambda, whether you could guarantee stability is an interesting question, and I don't know the answer to that exactly. I do know there are some really nice results in the literature that say the lasso actually is highly unstable in terms of which x's it selects, but that's a different measure of stability. That's stability on the discontinuous question of did you choose xj, rather than on the continuous question of what is the value you predicted for y. So I'm not sure.
There must be a phase transition then of the lambda. If it's unstable for lambda equals 0, if it's stable for lambda large identically 0, there has to be a non-zero lambda which goes from unstable to stable.
Yeah, that's a great question. I would expect empirically that that's the case. I don't know to what extent that's, I don't know like any theory that quantifies that, but yes, I would expect that this sort of like, epsilon that measures how unstable you are or whatever is going to sort of monotonically, I would guess, change over that path. I think that's correct.
So when I thought about stability, you get kind of defeated immediately, seemingly by squared error loss, which is the most common regression application, in the sense that it's not Lipschitz and it's not bounded. So is that an aspect of the stability result as far as in your experience? Like you have to make some sort of a bounded domain to your features.
So
you have to impose instructions which are bounded.
So in the second part of the talk, where I'll talk about why bagging is stable, our main results are for the bounded output setting where your predictions are bounded. We're working on stability of the prediction, not of the loss. Right. So like the fact that it's squared doesn't affect us. But for unbounded things, we do have some results, but they're like a bit more messy, so I didn't put them on the slides. You can do things, but effectively it means that you're like that your parameterization epsilon of like how much stuff changes is going to dynamically scale with like the range that your data lies in. So it is sensitive to that for sure. Okay. All right. So let's talk about why testing stability is hard. So what does it mean to have a black box test of stability? So again, I'm thinking about machine learning settings where my algorithm is too complex to analyze theoretically. And so I'm just going to examine its performance empirically. For example, maybe I will bootstrap samples from my data, or I will generate simulated samples, which I generate in a way that I believe is similar to the distribution of my data. And I do that as many times as I like. I run the algorithm on those data sets. I also run the algorithm on those same data sets with 1 point removed. And I just empirically look at whether stability seems to be happening or not. What I'm not allowed to do is look inside the black box. So effectively, like, you can push the button that calls the code, but you cannot open the file and read the code, is the way that I think of it. So I cannot actually see what the algorithm is doing, such that I could say, like, for example, what's the supremum of how much it could change if I add any data point. Because calculating this type of supremum would assume that I can search over uncountably many X prime, Y prime data points that I could add to my training set. So effectively, we're not actually assuming a computational budget. You can call it as many times as you like, but you can't call it like uncountably infinitely many times. Okay, so what do we want to produce in this setting? We want to construct a binary output, so a 0 or 1. A 1 indicates that the algorithm I'm testing, I believe it is stable, and a 0 indicates that I'm not sure. Now, just like in standard hypothesis testing, in the frequentist sense, I'm going to treat this as an asymmetric problem where I'm going to be really careful about one type of error, and then I'll see how much power I could get the other way. So I want validity in the sense that for any algorithm that's not stable, and again, stability here is statistical. It's a property of an algorithm and the distribution. So what I really mean is for any A and P that's not stable at sample size n, I would like a bounded by alpha probability of falsely declaring it to be stable, where this probability is with respect to the data that was inputted to my test. On the other hand, this test is useless if it doesn't have power. So I'd like to know that if the algorithm and distribution, if that pair AP is stable, then I'd like to have a higher than alpha chance of declaring it to be stable, because otherwise I'm just flipping a coin. Now I cannot hope for this to be always true. There's going to be some stable algorithms that are very close to an unstable algorithm, and I cannot tell them apart reliably. I just want this to be true for like nice A or nice A and P. It would be good to be able to characterize for what algorithms and distributions can I actually have meaningful power. So this is the goal. Okay, now in the interest of time, I'm just going to skip over this. Basically, this is a formal definition of what it means to be a black box test. And all it means is that I generate data, new data, as a function of my existing data. So for example, my existing data is bootstrapped to generate a new data set. And then I can run the algorithm on that data set. And then I can make whatever decisions I want to make, like let me sample more X's from this region of space or whatever. And I can iterate that as many times as I want. And at the end of the day, my output 0 or 1 is a function of that exploration process that I did. Okay. So let's start with a baseline. What is the simplest thing we could possibly do? And then let's try to beat it. So here's the baseline. It's a binomial test. So how much data I have is not necessarily my sample size n. So if my question is this algorithm stable when you train it on 100 data points? Maybe I have 200 data points with which to answer that question. So let me use kappa to say how many batches of data do I have? So DL is my available unlabeled data, labeled data. DU is my available unlabeled data. And kappa is the number of batches I have where I can construct a batch of n labeled points plus 1 additional X value to be my test point. So for example, if I have 200 data points, but I'm asking about stability when you train on 100 data points, we would have kappa equal to 2. Okay, so here's the binomial test. First, I'm going to split the data into these batches. So this is basically independent data sets of size n plus 1 test point. Then I'm going to fit the model and fit the model with 1 training point removed on each one of the batches. I want to point out that I'm not fitting all n leave one out models. I'm just removing 1 training point and that's it. So this is not using the data very efficiently, but at least it's computationally efficient. I'm going to check whether the prediction is large or small. I'm going to compare it to epsilon. And each one of those is independent because these are disjoint batches of my data. So I can then see how many of my perturbations were larger than epsilon and compare that against the binomial distribution with probability delta. So remember, the question is is there more than delta probability of the perturbation being more than epsilon? That would mean the algorithm's unstable. So I'm comparing it to the binomial distribution, and the question is the number of perturbations that I saw which were large small enough that I can conclude that probability is less than or equal to delta. So I can compare it to the binomial distribution with kappa, or rather kappa rounded down, as my number of batches, and delta as the parameter value that is kind of my null here. I want to prove that it's less than or equal to delta. Okay, so this test is valid. It's valid just by construction. Basically, the batches are independent from each other, so the binomial distribution is literally the correct distribution. This is a distribution-free test, because no matter how the data behaves, my question isn't about the data itself. My question is about how frequently does this event occur? And so that's just like a coin flip, and I'm only testing whether that coin flip's probability is about above delta or below delta. So it's valid universally over any algorithm. Now, what's its power? The bad news, and this is not unexpected, the power is very low if kappa is small. So for example, kappa is 2 because I'd like to test for size 100 and I have 200 data points. The delta parameter in any typical problem is going to be small, like at most 0.1, because I'm not really interested in saying, yay, it's stable, because at most 50% of the time the perturbation is large. I would like to define stability with a really small delta so that I know most of the time the perturbation is not large. So what this means is that my power is not much higher than alpha. It's not much higher than random, because at best, it's alpha times 1 over 1 minus delta raised to like the power 2, or however many batches you have. So this power calculation holds in a particular regime, basically the regime where alpha and delta are both pretty small. So that's the regime that we're usually thinking about, because we want our error levels to be small. So we should think of this roughly as telling us the power in any practical scenario. Okay, now this test is just a baseline, and it's super inefficient. We didn't resample, we didn't shuffle and repeat, we didn't use simulations, we didn't use bootstrap, we did none of those things. We just split the data into batches, and we didn't even like cycle through to do every possible leave one out model in each batch. Can we improve on this by sort of sacrificing computation time to try to use the data in a more detailed way? And unfortunately, the answer is no. The power that we just calculated for the super naive binomial test is actually the upper bound on power that you could get over any test at all. So this is for any black box test of stability, as long as it's universally valid, meaning for every unstable algorithm, it has at most alpha probability of incorrectly saying, actually, it is stable. So I just want to pause to interpret this result. So the upper bound is the same as binomial, at least in the regime where alpha and delta are small. This result does not mean there are some stable algorithms for which my power is low. This is a universal result. It says for every single stable algorithm, this is an upper bound on the power. So there's no such thing, this tells us, there's no such thing as a nice algorithm that's so obviously stable that you can construct a test to detect that and still be valid distribution free. This basically tells us that every stable algorithm is indistinguishable from an unstable algorithm. And so you cannot have power in this test unless you are willing to make more assumptions. Okay, so what does this mean? It means that it's impossible to gain information by calling A more times than the binomial test. Like simulating data and running A again does not help. So why? Because in my mind, like, of course it helps. I'm simulating and I'm observing what it does. Of course, I'm learning something about A. Here's the reason that it doesn't help in the theory. The reason is that when I simulate data and I run A, the reasoning in my mind is the simulated data is not exactly the same as the real data, but it's close enough, like in some kind of distributional sense. The distribution is close to the distribution of the real data. So the performance of A should be similar to the performance of A on the real data. That's what we think. When we think that, we are implicitly placing a continuity assumption on A, that when you feed it similar data, you get similar stability properties. If you want to be assumption free, A could be completely discontinuous in terms of you slightly perturb the data that goes in and all of a sudden you get something much more stable or much less stable coming out. If we don't want to place assumptions on A, this is the best we can do. Okay, so I know I'm short on time, so to give a 2-second proof of the sketch, The idea basically is that for anything that's stable, we're going to construct something super similar that's not stable, but it's so similar that on a finite training set, you cannot tell them apart. So for example, if we want to prove the part of the upper bound that comes from the limit in how much labels data you have, I'm going to construct a distribution that most of the time just samples from P, but a small fraction of the time replaces the actual value of Y with like a particular planted value of Y that indicates, dear algorithm, please corrupt the output for this data set. Then what the algorithm does is if it sees the corrupted value planted anywhere in the data set, it's going to output a corrupted prediction to make things unstable. Whereas if the majority of the time it doesn't see that corrupted value anywhere in the data set, it's just going to return to you whatever the algorithm that you are actually using would have returned to you. So this is constructed to basically be similar enough to the original A that I cannot tell the difference empirically, but different enough so that stability is violated. And therefore, my test has to return a 0 most of the time. Okay, I'll skip the rest of the details. All right, so to summarize, what this tells us that if we don't make continuity or whatever assumptions on A, then more sophisticated strategies that we know are teaching us about the algorithm cannot be theoretically shown to be teaching us anything about the algorithm because of these sort of degenerate constructions that say, well, if you're going to make no assumptions, then the binomial test is the best that you can do. So that might lead us to ask, like, what are some mild assumptions that we could make in order for stability to become testable? Or alternatively, let's not change our assumptions. Let's ask, is there a different version of stability that maybe is testable, even though this one is not? But if we're not willing to make either of those compromises, instead, could we take some kind of pre or post processing step that makes an algorithm stable, even if potentially it was unstable before, or at least we couldn't prove that it was stable before? So this leads into the second part, where basically our question now is there anything you can do, since we can't test stability, is there anything you can do to like retroactively create stability when you already ran an algorithm and it may or may not be stable, but it's the one that you want to use? So this leads into part 2. Let me pause again to ask if there's any questions. I'm sorry, could you speak up, please? If we do, sorry. Oh, leave 2 out. So actually, sort of leave more than 1 out version of stability is something that came up in some projects my group has been working on recently, where requiring stability to leave a small fraction out rather than 1 is useful for certain downstream applications. So that's a very practical direction. I think it will lead to a lot of downstream implications that leave 1 out stability is insufficient for. But on the flip side, if we're only asking, can we test it? Leave 1 out is sort of the like most stable of any of those. So like if we already cannot test leave 1 out, then probably like it's also impossible to test leave K out or whatever. So in terms of testing, I think the same results will go. In terms of what stability gives you, I think leave K out potentially could give you a lot more downstream than leave 1 out can. Thanks for the question. Okay. So what are we doing in this second part? So this is joint with Jake Soloff and Becca Willett. So in this second part, what we were investigating is there, oh, I'm sorry, yes.
First part, stability, we're studying under very weak conditions. In the old days, the scientific was called consistency of the predicted stress, which is also not testable.
Right.
Do you see any connection between the two, or are there situations where stability boils down to consistency?
So I think consistency is strictly stronger in the sense that consistency, the way I think of it, would generally mean that if I replaced my entire training set with a fresh draw, I would get a similar answer. Whereas stability is only requiring you to replace 1 point. So there's going to empirically be lots of settings where stability holds, but consistency fails. In terms of like why they're not testable, I think the ideas under the hood of like proving why they're not testable probably have a lot in common. But I think that empirically sort of what we observe for even methods like lasso, let alone more complex and more modern things. We observe a lot of settings where stability seems to hold even when consistency does not seem to hold, in the sense that like stuff jumps around a lot, but much, much less if you only replace one data point. So I think the distinction between those two frameworks is useful because even if we can't test it, I do think it describes our empirical observations of like many algorithms. But in terms of analyzing them, I agree with you. I think this has a lot in common. And I think a lot of tools for analyzing these things overlap for sure. Other questions? Okay. So I apologize in advance for rushing through what I'm about to rush through. So, okay, so what we were basically looking at is that bagging, so basically ensembling, bootstrap and aggregate or other versions of that, is something that empirically is used a lot, both for stability explicitly, like it's been known empirically that bagging makes things more stable, but also for lots of other reasons, like it just reduces variance, it improves accuracy, and so on. So what we wanted to try to understand is like theoretically, what is the relationship between bagging and stability? So just to formalize this, for bagging, what you do is you sample subsets of your data. You can sample it uniformly with replacement, uniformly without replacement, or there's other schemes as well. You fit models for each subset that you sample, and then you aggregate those models to return the final fitted model. So here in this talk, I'm going to be focusing on averaging as the mechanism for aggregation. Obviously, for something like classification, that might not even make sense. So far, we have studied averaging, but I think potentially these ideas could be extended to other forms of aggregation as well. Okay, so here's the most common options. That classical bagging, usually just called bagging, so you sample with replacement. Most often you run this with m equals n, meaning you keep the same sample size, but you sample with replacement. The important parameter will come up later in the theory is p. This is the probability of any given data point being in any given vect. You can also do sub-bagging sampled without replacement. Here, a very common option is to cut the sample size in half, so sample n/2 out of n without replacement. The parameter p here, again, the probability of any given item being in any given bag is just the ratio m/n. This appears in a ton of applications in statistics. For example, random forest, variable selection with the stability selection procedure, Bayesian inference as well, and many more. So this is used very, very broadly in statistics and machine learning. Theoretically, it's been studied a ton. So it's been studied for its favorable properties of smoothness, variance reduction, robustness, and many more. And there's some preliminary results in the literature about how it creates stability in certain settings. There's a lot of other results about how bagging specific algorithms create stability, like random forests is a bagged procedure. But we're interested generically, can any algorithm become stable if you place bagging as a post-processing step on that algorithm? Okay. So here's some empirical evidence that this phenomenon is universal across different base algorithms that get bagged. So we have logistic regression, neural networks, and regression trees. In each of these, the red is dispersed histogram is the perturbation of how much your prediction moves when you leave one out at random in the training process, versus blue, which is much closer to 0. Same question, but for the bagged version of that algorithm. So you can see basically the same trend for 3 very, very different base procedures A. Okay, now we're going to change our definition of stability. Previously, we were working with a statistical definition where stability was a property of A with respect to data from P. Now we're going to be working with stability with respect to any data set. So an algorithm is stable if when you have any data set and you remove one training point at random, so this gets back to a question that was asked earlier, the probability of a perturbation being greater than epsilon is bounded by delta. Again, I'm writing this deterministically, but you can also define this for randomized algorithms as well. This is basically saying how many data points I are influential enough on this prediction problem that you move by more than epsilon. At most, delta fraction of my training points are allowed to be that influential. Okay, so here's our main result. It says that no matter what the base algorithm is, as long as its outputs are bounded, it always satisfies stability after bagging for any epsilon and delta that have this scaling. So basically, epsilon and delta can go to 0 with n when you're doing something like classical bagging, where you sample n out of n with replacement, when you're doing something like sub-bagging, where you sample n/2 out of n with replacement. Stability is guaranteed with your epsilon and delta going reasonably quickly to 0, regardless of whether the original algorithm that you're applying bagging on is completely unstable. Again, we can do a randomized A. This theorem, just for cleanness of the statement, is as the number of bags goes to infinity, the results are for finite B as well. And if you're willing to get a somewhat messier result, you can allow the output to be unbounded, but here I'm just stating the simplest case. Okay, so what are some implications? You can do proportional sampling, so like n over 2 out of n. In that case, you get this scaling for the delta and epsilon for which stability is guaranteed. There's some prior work in the literature for massive subsampling where you sample a vanishing fraction of your data. This is practical when n is like 10 million and I can't run my model on a sample that large. But if n is limited and data is precious, what's most interesting to me is this minimal subsampling regime, where you could, for example, remove a random square root n samples from your training set and still be guaranteed stability. So this is interesting. You can train on nearly the exact same data set and still be guaranteed to get stability. Okay, so I will skip the proof sketch in the interest of time and let me just show you empirically. So for neural networks, the black dashed line in all of these figures is the theoretical guarantee that says how stable are you after bagging. What this says is that for any delta and epsilon above the line, you're guaranteed to be at least that stable. What the curves show is what is the best delta and epsilon for which the algorithm actually does satisfy stability. So you make delta bigger, it makes epsilon smaller, and vice versa. So the red curve is neural networks before bagging. It is unstable. The curve is high in the plot. The blue is after bagging. It's more stable. It's lower in the plot, smaller delta and epsilon. And it's also satisfying the theory. It's below the black dashed line, which is showing the theoretical guarantee. Same kind of picture for regression trees. Once you bag them, you get a random forest. And interestingly, for logistic regression, depending on the N versus D regime that you're in, the original algorithm, the dashed line, might be highly unstable or actually quite stable. But either way, after bagging, you get something that's quite stable because the theory says basically, no matter where you started, you will end up below the black dashed line. Okay. Now, we can also show that the scaling that we get is optimal in the sense that you cannot get a better result for delta and epsilon that would be universally valid over any algorithm that you then apply bagging to. So we can construct an algorithm whose delta and epsilon that's like the best stability that it achieves up to a constant is the same as our guarantee. So this tells us, in the picture, it sort of shows it more clearly, that just up to a constant, the guarantee, which is the blue curve, you're at least this stable for any bagged algorithm, is up to a constant as good as the best you can do, because the red curve is for the specific algorithm we constructed, how unstable was it? And the gap between them is not too big. We're off by only a constant. Okay, so just to skip ahead, let me just say one last thing before I wrap up, which is that, as was asked before, are we pulling out a data point at random from the training set, or are we pulling out like the most influential data point from the training set? And a lot of the literature studies this more worst case version of stability, which says that you're not allowed to have even a single influential data point. Influential meaning the perturbation is bigger than epsilon, whereas our version of stability says the fraction of influential data points can be at most delta out of your training set of size n. If you have this worst case definition of stability, you do get stronger guarantees downstream, but unfortunately, it's much harder to prove and it's much less realistic empirically. And in particular, we can show that we definitely cannot get the same kind of stability results for bagging if you have P, which again is like the subsampling ratio. So like if you draw N over 2 without replacement, P is a half. Stability will hold in this worst case sense for epsilon equal to like a half, but we want epsilon to go to 0. We can prove that there exists an algorithm for which after bagging, it is not stable at any epsilon smaller than 1/2 or whatever your subsampling ratio is. So it's really important that when we ask, is bagging stable, we're willing to accept the weaker notion of stability where you leave a data point out at random. Okay, so to wrap up, what we see is that bagging has this universality property. No matter what algorithm you apply it to, after you apply it, you're guaranteed to have stability. And this is nice because basically, if your algorithm was already stable, bagging, especially if you do minimal subsampling, shouldn't reduce the quality of your output. It might make it better, it might make it slightly worse, but it shouldn't change it very much. On the other hand, if you are unstable, maybe after bagging the output is really different, but that's good because it made it stable, whereas previously it failed this sort of natural condition of stability that we want. So downstream, this means that if you use things with bagging built in, you're automatically guaranteed to have generalization properties, predictive inference properties, and many more things. So we've got lots of open questions. We've really studied only like a narrow slice of definitions of stability relative to what's in the literature. We'd love to understand better how they fit together and how bagging performs relative to all of them. As I mentioned, averaging makes sense for aggregation in some settings like regression, but what if you're in classification? So that's an important open question as well. And we can also consider structured prediction problems where the output isn't real valued, but is instead like an image or a block of text or something like that. What does stability even mean in that context? And I think given sort of the current space we live in of like how machine learning algorithms are used, this is something that we really need to try to understand. Okay, so with that, let me wrap up, and thanks for all your questions so far and look forward to your feedback.
Follow up on the last question. So you might say something like you have a regression problem in quantitative regularization during different disease papers. So I was wondering if you have any also when you are deciding that what goes wrong or why you can't do something.
Yeah, that's a great question. So what's actually special about RIDS is not the convex regularization, but the strong convexity of the regularization. So you could certainly add an L1 penalty on top of that. But if you only have the L1 penalty, I don't know if there's a straightforward way to prove stability like there is for strong convexity in the regularizer. Great question.
In the interest of time, let's wrap up the question.
So we have small ceremony. Let me first say something about this award. It is the great J. Carroll Award, Young Investigator Award, that was established in honor of Dr. Raymond J. Carroll, Chief and Stuart A. Carroll, KTP Chair in Statistics, Distinguished Professor of Statistics, Nutrition, and Technology, for his fundamental contributions in many areas of statistical methodology and practice, such as measurement error models, non-parametric and semi-parametric regression, nutritional and genetic epidemiology. Carroll has been instrumental in mentoring and helping young researchers, including his own students and postdoctoral trainees, as well as others in the statistical community. Dr. Carroll is highly regarded as one of the world's foremost experts on problems in measuring error, functional data analysis, semi-parametric methods, and more generally, on statistical regression modeling. His work, characterized by a combination of deep theoretical effort, innovative methodological development, and close contact with science, has impacted a broad variety of fields, including marine biology, laboratory assay methods, econometrics, epidemiology, and molecular biology. In 2005, Raymond Carroll became the first statistician ever to receive the prestigious National Cancer Institute Method to Extend Research in Time, acronym MERIT, award for his pioneering efforts in nutritional epidemiology and biology, and the resulting advances in human health. Less than 5% of all national institutes of health funded investigators made selection for this highly selective award, which includes up to 10 years of grant support. The Carroll Young Investigator Award is awarded biennially in odd-numbered years to a statistician who has made important contributions in the area of statistics. It's time, Rina, Barber. So let me present Rina with black.